Section 1 Introduction. Let's dive into the fascinating problem of constructing a three-dimensional scene from a single two-dimensional image. Since a good part of the 3D scene is hidden from view, there are countless possible 3D scenes that could generate the given image. This complexity is due to the conversion from 3D to 2D, objects obstructing each other, and a limited field of view that leaves large portions of the 3D scene unseen. Given the challenging nature of this task, it would be beneficial for a reconstruction algorithm to be capable of generating multiple realistic 3D scenes that align with the 2D image, filling in the unseen parts in believable ways. In the past, techniques for completing missing data, like filling in gaps in 2D images, were trained on large collections of complete images and their partial counterparts. However, these methods struggle when applied to 3D scene completion because gathering a substantial dataset of complete 3D scene representations is extremely difficult. This issue of completing 3D scenes from 2D images, often termed inverse graphics, is an example of a broader category of problems known as stochastic inverse problems, which pop up across various scientific fields whenever we try to understand the world through limited observations. In this paper, we present a new framework based on diffusion that can handle these types of problems. This framework lets us generate multiple instances from a pool of signals that match a set of partial observations created by a non-reversible, typically nonlinear, forward model. For example, in inverse graphics, we learn to generate 3D scenes from an image without ever having seen paired observations of images in 3D scenes during training, nor direct observations of 3D scenes. While advancements in deep learning for generative modeling have been impressive, this particular challenge remains unsolved. Traditional techniques, like variational autoencoders and conditional neural processes, have so far been unable to accurately represent the complex distributions needed in tasks like inverse graphics, often being restricted to simpler datasets. On the other hand, emerging diffusion models allow for sampling from intricate conditional distributions but need samples from the output distribution for training, such as complete 3D models. Some recent work in inverse graphics uses a two-step process, first recreating a large dataset of 3D scenes, and then training an image conditional diffusion model to sample from the pool of scenes. In contrast, other researchers have trained conditional diffusion models to sample from the pool of novel views of a scene, only requiring image observations during training. However, these methods do not directly model the distribution over 3D scenes and, therefore, can't generate samples from the distribution over 3D scenes in alignment with an image observation. To get a consistent 3D scene, an expensive post-processing stage is required. A significant exception to this is the recently proposed render diffusion, which shows it's possible to train an unconditional diffusion model over 3D scenes using only single-view images. While such models can generate conditional samples, they're limited to simple distributions, like single objects in standard orientations. Our main contribution is a fresh approach that combines any differentiable forward model, which explains how partial observations are made from signals, like 2D image observations from 3D scenes, with conditional denoising diffusion models. When we sample an observation from our model, we also simultaneously sample the signal that created that observation. This method has several benefits that make it highly effective for solving intricate stochastic inverse problems. First, our model is trained in one go and eliminates the need for a two-step process that initially requires the reconstruction of a vast dataset of signals. Second, our model directly produces a variety of samples of the signal of interest. For instance, in the inverse graphics setting, our model directly provides a broad range of 3D scene samples that align with an observation and can then be displayed from new views with guaranteed consistency. Lastly, our model effectively utilizes domain knowledge in the form of known forward models, such as differentiable rendering, with all the assurances that such forward models provide. We put our approach to the test on three demanding computer vision tasks: inverse graphics, the focus of this paper, single image motion prediction, and GAN inversion. In summary, our key contributions are: 1. We propose a novel method that combines differentiable forward models with conditional diffusion models, replacing previous two-step methods with a conditional generative model trained end-to-end. 2. We apply our framework to build the first-ever conditional diffusion model that learns to sample from the pool of 3D scenes trained only on 2D images. Unlike earlier work, we directly learn image-conditional 3D radiance field generation, instead of sampling from the pool of new views conditioned on a context view. Our treatment of inverse graphics goes beyond merely applying the proposed framework, contributing a novel 3D structured denoising step that takes advantage of differentiable rendering for both conditioning and for the differentiable forward model. 3. We formally demonstrate that under certain assumptions, as the number of observations of each signal in the training set grows indefinitely, the proposed model maximizes not only the likelihood of observations but also the likelihood of the unseen signals. 4. We showcase the effectiveness of our model for two more downstream tasks with structured forward models: single image motion prediction, where the forward model is a warping operation, and GAN inversion, where the forward model is a pre-trained style GAN generator. Section summary. The problem of reconstructing a 3D scene from a single image is challenging due to the unobserved parts of the scene. Previous data completion methods are not suitable for 3D scene completion, and a diffusion-based framework is introduced to tackle this problem by enabling sampling from a distribution of signals consistent with partial observations generated from the signal by a non-invertible forward model. The proposed approach integrates differentiable forward models with conditional diffusion models, replacing prior two-step approaches with a conditional generative model trained end-to-end, and is validated on 3 challenging computer vision tasks. Section 2 Method. In the method section, we will explore the process of observations derived from various underlying signals. Let's denote the observations as O, the signals as S, and the parameters related to the forward model, the mechanism that transforms signals into observations, as phi. Essentially, the concept can be simplified as O being generated from S through a defined forward process, taking into account the parameters phi. These parameters correspond to the observation O and are unique for each one. A critical point to understand is that every observation could be incomplete or partial, suggesting that multiple signals might result in the same observation. To illustrate this with a practical example, let's consider the concept of inverse graphics. Here, O is represented by image observations of 3D scenes, S, and the camera parameters are R phi. Index J is used for different scenes, and index I for different observations within a particular scene. The forward process in this scenario is represented by the rendering function, which transforms our 3D scene into a 2D image. Notably, a single image can correspond to an infinite number of 3D scenes, due to the projection from 3D to 2D and the fact that a single image only reveals a portion of the 3D scene. However, if we could capture every possible image of a 3D scene, the scene could be uniquely identified. Moving forward, we aim to create a model that can produce a range of signals, consistent with a previously unseen observation. The objective is to model the conditional distribution P, S, O, phi, which represents the probability distribution of signals given an observation and the parameters. We're making a few assumptions here. 1. We can apply the forward process in a differentiable manner. 2. We have a large dataset of observations and the corresponding parameters, represented as O, phi. 3. In our training set, we have multiple observations for each signal. However, crucially, we are not assuming direct access to the underlying signal that created a particular observation. In other words, we don't have direct access to tuples of O, phi, S. We also don't assume any prior knowledge about the distribution of the signal, meaning we don't have a dataset of signals that can be used to train a generative model to sample from an unconditional distribution over signals. We then look at recent developments in deep learning, where denoising diffusion models have shown promising results as powerful generative models. These can generate diverse samples from complex, multimodal distributions. Motivated by this, we plan to use such models to determine P, S, O, phi. Yet, we face a challenge because current approaches can't be trained if we don't have direct access to the signals S. We'll further discuss denoising diffusion models and this limitation in the next part. Section summary. The section discusses a method for training a model to sample from the distribution of signals that are consistent with a previously unseen observation. The method assumes access to a differentiable implementation of the forward model, a large dataset of observations and corresponding parameters of the forward model, and several observations per signal in the training set. The method leverages denoising diffusion probabilistic models to model the conditional distribution P, S, O, phi, but existing approaches cannot be trained if signals S are not available. Section 2.1 Background. Denoising diffusion probabilistic models and their limitation. We're delving into the realm of denoising diffusion probabilistic models, DDPMs, and their limitations. DDPMs are a type of generative models that learn how to draw samples from a distribution by progressively reducing noise within these samples. Imagine we're trying to model a distribution p_theta over certain samples. In this scenario, a step-by-step, or Markovian, forward process is used to introduce noise into the data. Think of it like this. It's as if we're starting with our data and deliberately blurring it. The level of blur or noise we introduce is governed by parameters referred to as beta_t, where t ranges from 1 to t. These parameters control what we call the variance schedule. What a DDPM does is learn the reverse of this blurring process. It starts with samples drawn from a standard normal distribution, p, x_t, and then gradually removes the noise, transforming these samples back into the original data. We use a special neural network with adaptable parameters to learn how to perform this denoising process. Moreover, it's possible to model something known as conditional distributions, where we consider the impact of additional factors or conditions on our samples. For instance, imagine we're denoising an image, and we also want to take into account the lighting conditions under which the image was taken. The denoising model takes this condition into account as well when doing its work. However, the initial process of introducing noise remains unchanged. Yet, there's a significant limitation. Existing DDPMs can't learn to sample from certain distributions, even if we don't consider additional conditions. This issue arises because of the need to calculate the Markovian forward process, the initial introduction of noise. Remember, we don't have any signals to add noise to, which is a fundamental part of training a denoising neural network. Put simply, we can't compute something we can't observe. Hence, without any observable signals, the Markovian process becomes impossible to calculate, presenting a significant hurdle for current DDPMs. Section summary. Denoising diffusion probabilistic models are generative models that learn to sample from a distribution by denoising samples. The model learns the reverse process of a forward Markovian process that adds noise to the data. However, existing denoising diffusion models cannot be trained to sample from an unconditional distribution or from P, S, O, phi, because no S is directly observed, and thus, Q, S_T, S_T1, cannot be computed. Section 2.2 Integrating denoising diffusion with differentiable forward models. We're introducing a new class of denoising diffusion models. These models are designed to represent a distribution of signals based on a given observation, which we'll denote as S given O, with a context parameter phi. Our major contribution here is the integration of a differentiable forward model into the process of iterative conditional denoising. This enables us to add noise to, and subsequently denoise, the observations while preserving the ability to sample from the underlying signal that generates that observation. Our model is trained using pairs of context and target observations of the same signal. These are denoted as O_context and O_target. In line with standard diffusion models, we have a forward process where O_target at time t is dependent on O_target at time t1. Following a normal distribution centered at square root of 1 minus beta_t times O_target at t1, with a standard deviation of beta_t times identity matrix. We also have a reverse process where we denoise O_target based on O_context. However, unlike typical diffusion models, we predict an estimate of the underlying signal S at t1 first and then map it to an estimate of the denoised observations using the differentiable forward model. Here, the estimated O_target at t1 is considered the clean observation. We have chosen constants to match the total noise added by the forward process at time t1. At testing time, we sample a signal by iterating the forward and reverse process equations, starting with O_target at the end time t following a normal distribution centered at 0 with identity matrix as the standard deviation. Importantly, our models define a generative model over the underlying signal through these processes. Moving on to the loss function, we train our model to maximize the likelihood of observing O_target given O_context and the context and target parameters. We use a simplified objective from DDPM, denoising diffusion probabilistic models, for our loss function. In this case, we compute the estimated O_target at t1 by deriving O_target at t from the ground truth using the forwards process, then using the denoise and forward functions. Regarding the conditional distribution over signals, it might not be obvious that the learned distribution over signals aligns with the true distribution due to the complexity of the reverse process. However, we argue that our model will asymptotically learn the true conditional distribution over signals. We have a formal proof for this in the supplement. The crux of the proof is, if we assume that any signal S can be reconstructed from all possible observations O_phi of S, and the loss is minimized exactly on the true conditional distribution of target observations when the number of known observations per signal goes to infinity, then the distribution over signals discovered by our model agrees with the true distribution. Section summary. The authors introduce a class of denoising diffusion models that directly model the distribution of signals given an observation. They integrate a differentiable forward model into the iterative conditional denoising process, enabling noise addition and denoising of observations while sampling the underlying signal. The model is trained to maximize the likelihood of the target observation given the context observation, and it asymptotically learns the true conditional distribution over signals. Section 3. Prior work on latent variable models for inverse problems. The preceding research in the area of latent variable models for inverse problems is significant. Key players in this field are variational autoencoders, normalizing flows, and certain neural processes. These are basically models with hidden variables that, when paired with structured forward models, are trained to draw samples from the unseen signal distributions based on their observations. But in practice, they don't always succeed in accurately modeling intricate signal distributions. For example, in the realm of inverse graphics, the scope of these models has been somewhat restricted to artificial 3D scenes. Generative adversarial networks, GANs, on the other hand, can be taught in conjunction with differentiable forward models, and have shown promising results when it comes to generatively modeling unseen signals without any specific conditions. In similar vein, diffusion models have been exploited for generative modeling without any conditions using differentiable forward models, as evidenced in some simultaneous research. Nonetheless, these unconditional models do have their limits. They're mainly confined to tight distributions, and there hasn't yet been any comparable, high-quality generative modeling demonstrated for conditional cases. Diffusion models that are trained directly on signals have proved to be quite effective for various inverse problems. These include tasks like super resolution, inpainting, and medical imaging. What these methods do is use the learned understanding of the data distribution to retrieve the hidden signal. They accomplish this via a plug-and-play method, incorporating the diffusion model with a forward measurement process according to Bayes' rule. What makes these methods so versatile is their ability to easily adjust to new inverse problems without the need for additional training. However, they differ from our models in a significant way. They rely on having direct oversight over the signals, which means they need large datasets to work from. Section summary. Latent variable models like variational autoencoders, normalizing flows, conditional and attentive neural processes can be combined with structured forward models to learn to sample from the distribution of unobserved signals from observations, but they have limitations in accurately modeling complex signal distributions. Generative adversarial networks and diffusion models have yielded impressive results in unconditional generative modeling of unobserved signals, but no conditional generative modeling of similar quality has been demonstrated. Diffusion models trained directly on signals have been effectively applied to diverse inverse problems such as super resolution, inpainting, and medical imaging, but they rely on direct supervision over the signals in the form of large datasets, unlike the models proposed in this paper. Section 4 Applications. In this section, we are going to explore 3 applications of our theoretical framework, particularly focusing on computer vision problems. These include inverse graphics, single image motion prediction, and GAN inversion. For each of these applications, we will explain the key models, data sources, benchmarks, and a quick summary of past research in the area. To begin, let's discuss inverse graphics. In this scenario, we're interested in a model that, given a single image of a 3D scene, allows us to generate samples from the distribution of possible 3D scenes that match the input image. Specifically, we hope to accurately reconstruct visible portions of the 3D scene, while filling in the unseen parts with plausible creations. Each sample we generate should offer a unique, plausible 3D output. Here, the signals represent the 3D scenes and the observations are 2D images, along with their corresponding camera parameters. The role we assign to inverse graphics in this context extends beyond a simple application of our framework. We integrate a differentiable rendering function and propose a novel approach for denoising in 3D. The result is a model that's capable of generating state-of-the-art conditional 3D scenes, which reflect real-world complexity. In terms of prior work, the field has seen several pioneering efforts. Earlier deterministic methods blurred unseen parts of the 3D scene in the context observations, whereas probabilistic methods have allowed us to sample from the distribution of novel views using only images. However, these techniques didn't allow for sampling from the distribution of 3D scenes, and instead, only provided novel view distributions. The generated scenes were not consistent when viewed from multiple angles, and a costly post-processing step was required to obtain a 3D scene. Some previous methods used a two-stage design, first reconstructing a dataset of 3D scenes, then training a 3D diffusion model. This approach was costly, as it required pre-computing large 3D datasets and a large number of observations per scene for high-quality results. Others, such as render diffusion and hollow diffusion, combine differentiable forward rendering with an unconditional diffusion model to enable the sampling of simple, single-object scenes. In our model, we adopt NRF, neural radiance fields, for the parameterization of 3D scenes. This implies that our signal is a function mapping a 3D coordinate to a color and density value. We use a feed-forward encoder to predict a generalized NRF, based on a set of context images and corresponding camera poses. Our model follows the pixel May-RF design, which first extracts image features from each context observation. Given a 3D point, Pixel NARF calculates its pixel coordinates in each context view and recovers corresponding features by sampling the feature map at these pixel coordinates. The signals are then parameterized using a multi-layer perceptron, MLP. We use a differentiable volume rendering as a forward model to render the scene from a camera with specific parameters. To generate the target view, we render the pixel NARF conditioned on the context and noisy target observations. The denoising procedure involves augmenting the noisy target with information from the context view. We generate conditioning information by rendering a deterministic estimate of the target view using only the context view. For uncertain target views, we propose rendering high-dimensional features in addition to the color and density values, to avoid creating a completely blurry image. The final 3D scene is generated by combining the context view and both the deterministic and noisy target views. Lastly, for loss and training, we employ a simple least squares term to measure the discrepancy between the generated and the actual target view. We also use several regularizers to discourage the generation of degenerate 3D scenes. Further details about these regularizers and the training process can be found in the supplementary material. Section Summary. The framework is applied to 3 stochastic inverse problems in computer vision, including inverse graphics, single image motion prediction, and GAN inversion. The inverse graphics application involves learning a model that can sample from the distribution over 3D scenes consistent with a single image observation, with a focus on faithful reconstruction of visible 3D regions and plausible generation of unobserved parts. The forward model is based on differentiable volume rendering, and a novel 3D structured denoise function is proposed to enable state-of-the-art conditional generation of complex, real-world 3D scenes. Section 4.1.1 Results. In Section 4.1.1, we discuss our experiment's results. We evaluated our methodology using 2 complex, real-world datasets. The first one, Co-3D hydrants, was employed to test our method on object-focused scenes. For 3D synthesis at the scene level, we utilized a tough dataset made up of indoor and outdoor videos of various scenes. We compared our method with the latest advancements in both deterministic and probabilistic 3D scene completion. The method that we chose as representative of deterministic methods is Pixel NARF, which uses a single image as input and creates a 3D scene deterministically. It's important to mention that our technique is pioneering in the probabilistic reconstruction of 3D scenes in a seamless process. Still, we drew comparisons with sparse fusion, a concurrent method that learns a generative model in image space over the novel views of a 3D scene. However, this approach requires a costly score distillation every time a multi-view consistent 3D scene is needed. Looking at the qualitative results, we demonstrate multiple 3D scene samples derived from a single image view in a given figure. When considering indoor scenes, there's a lot of ambiguity in large regions. We addressed this by sampling from the distribution of viable 3D scenes, yielding significantly distinct scenes with convincing geometry and colors. The object-centric scenes from Co-3D were accurately reconstructed, capturing the inherent uncertainty of the scene. Moreover, we utilized autoregressive sampling to generate larger 3D scenes and longer trajectories. This involved treating intermediary diffused images as additional context observations to sample another target observation. We used this approach to generate complete 360 degrees trajectories from the Co-3D results. Comparing our results with Pixel NARF and sparse fusion, Pixel NARF, as a deterministic method, resulted in blurry outcomes in uncertain regions. Sparse fusion, on the other hand, reconstructed scenes by score distillation over a 2D generative model. This was a high-cost optimization process and didn't yield natural-looking results. Finally, we analyzed our quantitative results. We evaluated the accuracy of novel views on the object-centric Co-3D dataset using 2 metrics, PSNR and LPIPS. However, for larger scenes with high uncertainty, these metrics aren't suitable since a broad array of novel view images could be consistent with any input image. For such cases, we reported FID and KID scores to assess the realism of the reconstructions. Our method surpassed all other techniques in the LPIPS, FID, and KID metrics, resulting in more realistic outputs. However, we saw slightly lower PSNR scores compared to PixelNRF. It's worth noting that PSNR tends to favor average estimates, and our model was evaluated using a single randomly selected scene for an input image due to computational limitations. Section Summary. The authors evaluated their method on 2 real-world datasets, Co-3D hydrants for object-centric scenes and a challenging dataset for scene-level 3D synthesis. They compared their approach with state-of-the-art deterministic and probabilistic 3D scene completion methods, and their method was the first to probabilistically reconstruct 3D scenes in an end-to-end manner. Their approach outperformed all baselines for LPIPS, FID, and KID metrics, achieving more realistic results. Section 4.2 Single Image Motion Prediction. In Section 4.2, we delve into the concept of predicting motion from a single image. The main idea is to devise a model that, when presented with a single still image, can predict all plausible pixel movements in the image. For instance, if we have an image of a person in the act of kicking a soccer ball, our model aims to forecast possible future states. This task, inherently uncertain, has multiple potential motion outcomes aligned with a single image. Our training utilizes a dataset of natural videos, but it's worth noting that we only view RGB frames, never directly witnessing the underlying motion, such as how pixels correspond over time. The training employs pairs of frames from the videos, captured within a short time span, which serve as our context and target observations. This problem has been explored in various studies where motions like optical flow, 2D trajectories, and human movement are extracted from a static image. However, all these approaches assume some supervision over the underlying motion. Our model learns to understand motion by learning about the characteristics and actions of different objects. This capability makes it a beneficial task for learning representations and can serve as a foundation for numerous downstream applications. The signal, denoted by S, in our model incorporates appearance and motion information in a 2D grid. At any given pixel, referred to as U, the signal is defined as having two components, the color value, and a 2D motion vector. We also employ a forward model, a warping operator, that can modify the motion magnitude of the signal. This operation is implemented using a differentiable point splatting method. As for the implementation, our design is depicted in an inset figure. We employ a 2D network that accepts the context frame, target frame at a time, t, and t, itself as inputs, and produces a motion map as output. This signal is then reconstructed with the context frame in the motion map. The context and target frames are reconstructed from the signal using the warp operation. The evaluation of our model uses both reconstruction and regularization losses, similar to inverse graphics. The reconstruction loss encourages a more accurate recreation of the image, while the regularization loss promotes a natural movement in the scene. We demonstrate the results in a figure where diverse motion flows are estimated from single images. By gradually changing the motion magnitude, our model can generate short video sequences, even though it was trained only on low frame rate video frames. We also attempted a deterministic baseline model that predicts a single motion field. However, due to the inherent uncertainty in the problem, this model invariably produces a motion field close to zero, regardless of the input image, and thus fails to extract any meaningful features from the images. Section summary. The goal is to train a model that can predict all possible motions of pixels in a single static image, using a dataset of natural videos. The model uses a warping operator to implement a forward model, and a 2D network to generate the motion map. The reconstruction and regularization losses are used for evaluation, and the results show that the model can estimate a diverse set of possible motion flows from monocular images. Section 4.3 GAN Inversion. This section is focused on GAN inversion, a process that refers to projecting images onto the generative adversarial network's latent space, a high-dimensional numerical space where the generator of the GAN can create new images. This is a well-explored field, and it has some fascinating applications, such as allowing users to edit images effectively by adjusting their latent representations. Our focus, however, is a bit different. We're looking at the problem of projecting partial images, or small visible patches of an image. We're trying to figure out how to represent the range of possible style GAN2 latent codes that match these small patches. This is an interesting problem because a number of different latent codes could match a given input. To achieve this, we're training our model without supervised data, that is, we don't use image latent pairs. Instead, we use pairs of observations consisting of small patches and the full images they come from. Let's talk about what has been done in this field so far. Most methods that focus on GAN inversion are trying to convert a whole image into a representation in the latent space of the generator. Some methods do try to reconstruct latent codes from small patches, but they use supervised training. The inversion process is not simple and usually requires some sort of regularization, or involves integrating the inversion with editing tasks to improve the quality of the inversion. We're also integrating the inversion process with an image inpainting task, and we're focusing on modeling the uncertainty of the GAN inversion task when only a partial image is available. To describe the structure of our method and the forward model we're using, let's consider a signal we denote as S, which lives in a 512-dimensional space. This signal is a latent code representing a W space of style GAN2 trained on a face dataset called FFHQ. The forward model takes the latent code and creates the image corresponding to it, using the generator of the GAN. Then, it extracts a patch from the generated image using parameters that define the patch's location. As for the implementation details of our method, we use a denoising network that takes in a small patch, a full image at a specific time, and the time itself as input. This network then generates an estimate of the style GAN latent code. Our loss function compares the image generated from this estimated code with the original image to gauge the accuracy of the inversion. As shown in our results, we produce diverse samples that match the input patch. We also compare our method with a baseline deterministic method that only generates one estimate. Although this baseline method also matches the input image, it doesn't account for the diversity of possible outputs. As a result, our method performs significantly better, as shown by our FID and KID scores, metrics used to measure the similarity and diversity between the generated images and the real images. Section Summary. The section discusses a method for projecting partial images onto the latent space of style GAN2 without supervised training. The method involves a denoising network that estimates the style GAN latent from small patches in images, and a loss function that compares the reconstructed sample with ground truth. The results show diverse samples that are consistent with the input patch, and significantly better FID and KID scores than a deterministic baseline.